There are two numbers that should be identical. They are both measurements of the same physical quantity, the rate at which the universe is expanding, expressed in the same units, performed by different methods using different instruments at different cosmic epochs. They are among the most precisely measured quantities in the history of science, and they disagree. The first number is 67.4. The second number is 73. In the units cosmologists use, kilometers per second per megaparsec, these two numbers describe how fast a galaxy recedes from us for every additional megaparsec of distance. A megaparsec is roughly 3.26 million light years. So 67.4 means a galaxy 1 megaparsec away is receding at 67.4 kilometers per second. A galaxy 2 megaparsecs away is receding at about 135 kilometers per second. The rate scales with distance. That scaling is the expansion of the universe. Both measurements are correct in the sense that both have been performed carefully, checked extensively, and confirmed by multiple independent teams using multiple independent data sets. Neither is likely to be a simple measurement error. The discrepancy between them, which astronomers call the Hubble tension, is approximately 8%. The statistical significance of the disagreement, given the precision of both measurements, is between 4 and 5 sigma. It is, in the language of physics, a serious anomaly. And then James Webb made it worse. The Hubble tension was already a significant problem before James Webb began science operations in 2022. But one of the main hopes for resolving it was that the Hubble Space Telescope measurements that produced the value of 73 might contain a systematic error related to the behavior of Cepheid variable stars, the pulsating stars used as standard candles to measure cosmic distances. Webb's vastly superior infrared sensitivity and resolution were expected to resolve this question definitively. If the Cepheids had been mischaracterized by Hubble, Webb would reveal the error and the tension would dissolve. Webb confirmed the Hubble measurements. In 2023, the team led by Adam Riess, one of the discoverers of dark energy and a Nobel laureate in physics, published James Webb Space Telescope observations of Cepheids in nearby galaxies. The Webb results were consistent with the Hubble results. The Cepheid measurements were not wrong. The tension remained. It got slightly worse. I want to take you through the full story of the Hubble tension because I think it is the most important unresolved problem in cosmology right now, more urgent and more specific than the general unease about the standard model that I described in the video about the James Webb and large-scale structure anomalies. The Hubble tension is a direct quantitative conflict between two precise measurements that both claim to measure the same thing. It requires a specific resolution. Either one of the measurements is wrong, or the standard model of cosmology is incomplete in a way that allows two different methods to give different answers for the expansion rate. And after a decade of searching, neither option has been convincingly established. Let me start with what the Hubble constant actually is, because the concept is simple, but the implications run deep. Edwin Hubble published his discovery of the expanding universe in 1929. By measuring the distances to nearby galaxies using Cepheid variable stars and comparing those distances to the velocities of the galaxies inferred from their spectral redshifts, Hubble showed that galaxies are receding from us with velocities proportional to their distances. The farther a galaxy is, the faster it is moving away. This proportionality, V equals h times d, is Hubble's law, and h is the Hubble constant, the constant of proportionality. Hubble's original estimate of h was approximately 500 kilometers per second per megaparsec, which we now know was dramatically too high due to errors in the Cepheid distance scale. Subsequent decades of refinement brought the value down substantially. And there was a long controversy between groups that favored values around 50 and groups that favored values around 100. The uncertainty was not in the measurements themselves, but in the calibration of the distance ladder, the multi-step chain of methods for measuring distances at increasing cosmic scales. The Hubble Space Telescope was launched in 1990 with the explicit goal of resolving this controversy. Its key project, led by Wendy Friedman, was a systematic program to calibrate the Cepheid distance scale and measure the Hubble constant. The key project published its final results in 2001, finding H0 equals 72 plus or minus 8 kilometers per second per megaparsec. The controversy was resolved. At least approximately, the Hubble constant was somewhere near 70. Edwin Hubble published his discovery of the expanding universe in 1929. By measuring the distances to nearby galaxies using Cepheid variable stars and comparing those distances to the velocities of the galaxies inferred from their spectral redshifts, Hubble showed that galaxies are receding from us with velocities proportional to their distances. The farther a galaxy is, the faster it is moving away. This proportionality, V equals h times d, is Hubble's law, and h is the Hubble constant, the constant of proportionality. I want to put Hubble's discovery in historical context because it was not obvious at the time, and the path to it was longer and more contested than the popular account suggests. In the early 20th century, the size and nature of the universe were genuinely uncertain. The debate between Harlow Shapley and Heber Curtis in 1920, now called the Great Debate, concerned whether the spiral nebulae were objects within our galaxy or separate island universes comparable to the Milky Way. Shapley argued they were within our galaxy. Curtis argued they were external galaxies. The question could not be resolved with the telescopes and techniques available at the time. The resolution came with the commissioning of the 100-inch Hooker telescope on Mount Wilson in California, then the largest telescope in the world. Edwin Hubble used this telescope to resolve individual stars in the Andromeda Nebula and other spiral nebulae, identifying Cepheid variable stars among them. By measuring the periods of these Cepheids and applying the period-luminosity relation discovered by Henrietta Swan-Leavitt, Hubble calculated the distances to the spirals and found them to be far beyond the boundaries of the Milky Way. The Great Debate was resolved. The spirals were galaxies, but measuring distances was only half the story. Vesto Slipher at the Lowell Observatory had been measuring the redshifts of spiral nebulae since 1912, finding that most were receding from us at high velocities. When Hubble combined his distance measurements with Slipher's velocity measurements, the pattern was clear. Velocity and distance were proportional. The universe was expanding. Hubble's original estimate of h was approximately 500 kilometers per second per megaparsec, which we now know was dramatically too high due to errors in the Cepheid distance scale. The problem was that Hubble was comparing Cepheids in the Milky Way calibrated by Shapley with Cepheids in other galaxies. But Shapley's calibration was based on a misidentification of certain variable stars, and the distance scale was off by a factor of several. Subsequent decades of refinement brought the value down substantially. Walter Baades' discovery in the 1950s that there were two populations of stars with different period luminosity relations doubled the distance scale overnight. Further corrections brought the Hubble constant down toward its current range. There was a long controversy between groups led by Alan Sandage, who favored H values around 50, and Gerard de Vaucouleurs, who favored values around 100. The controversy reflected genuine systematic uncertainties in the distance ladder that could not be resolved with pre-Hubble Space Telescope technology. The Hubble Space Telescope was launched in 1990 with the explicit goal of resolving this controversy. Its key project, led by Wendy Friedman, was a systematic program to calibrate the Cepheid distance scale and measure the Hubble constant. The key project published its final results in 2001, finding H0 equals 72 plus or minus 8 kilometers per second per megaparsec. The controversy was resolved at least approximately. The Hubble constant was somewhere near 70, and then a completely different method came along, and it gave a different answer. The Planck satellite, launched in 2009 by the European Space Agency, measured the cosmic microwave background, the relic radiation from the hot early universe, with extraordinary precision. The CMB contains a wealth of information about the early universe and about the cosmological model that describes its evolution. By fitting the detailed pattern of temperature fluctuations in the CMB to the predictions of the Lambda CDM model, the Planck team could infer the values of all the cosmological parameters, including the Hubble constant. The Planck satellite, launched in 2009 by the European Space Agency, measured the cosmic microwave background, the relic radiation from the hot early universe, with extraordinary precision. The CMB contains a wealth of information about the early universe and about the cosmological model that describes its evolution. By fitting the detailed pattern of temperature fluctuations in the CMB to the predictions of the Lambda CDM model, the Planck team could infer the values of all the cosmological parameters, including the Hubble constant. Let me describe the physics of the CMB acoustic oscillations in more detail, because understanding how the Hubble constant is extracted from the CMB is essential for understanding why the Hubble tension is so puzzling. In the first 380,000 years after the Big Bang, the universe was a hot, dense plasma of electrons, protons, and photons. The photons and electrons were tightly coupled through Thomson scattering, so the plasma behaved as a single fluid. Dark matter did not participate in this coupling. It exerted gravity but did not interact electromagnetically. Small density perturbations were present in this plasma from the very beginning, seeded by quantum fluctuations during inflation. These perturbations set the plasma oscillating, creating acoustic waves that propagated through the medium. The waves were driven by the competition between radiation pressure, which resisted compression, and gravitational attraction, which encouraged it. Dark matter, which provided only gravitational attraction, helped drive the oscillations on one side. At recombination, when the temperature dropped to about 3,000 Kelvin, the electrons and protons combined into neutral hydrogen. The coupling between photons and electrons ended abruptly. The acoustic oscillations froze in place. The photons streamed freely from this moment on, carrying with them the imprint of the acoustic oscillation pattern. This is the cosmic microwave background. The acoustic oscillations left a specific pattern in the CMB, alternating peaks and troughs in the angular power spectrum, corresponding to modes that were at maximum compression, maximum rarefaction, or intermediate phases at the moment of recombination. The angular positions of these peaks in the CMB power spectrum depend on the physical scale of the acoustic oscillations relative to the angular diameter distance to the last scattering surface. The sound horizon, the maximum distance that sound waves could travel before recombination, is a physical scale that can be calculated from first principles if we know the densities of all the components. It depends primarily on the baryon density and the radiation density in the early universe. For the standard cosmological parameters, the sound horizon at recombination is approximately 150 megaparsecs in comoving distance. The angular scale at which we observe the acoustic peaks in the CMB depends on the ratio of the sound horizon to the angular diameter distance to the last scattering surface. The angular diameter distance depends on the entire expansion history of the universe from recombination to today, which depends on all the cosmological parameters, including H0. This is why the CMB measurement of H0 is indirect. The CMB measures the angular scale of the acoustic peaks. The physical scale of the sound horizon is calculated from early universe physics. The Hubble constant is then inferred from the relationship between these two scales through the expansion history. If lambda CDM correctly describes that expansion history, the inferred H0 should match the locally measured H0. If it does not, either the model or one of the measurements must be wrong. The Planck measurement of the Hubble constant, published in 2013 and refined in subsequent data releases, gave H0 equals 67.4 plus or minus 0.5 kilometers per second per megaparsec. This is a strikingly precise measurement with an uncertainty of less than 1%, and it is strikingly different from the local measurements which had converged to values around 73 by the mid-2010s as the calibration of the distance ladder improved. The tension between these two values, 67.4 from the CMB and 73 from the local distance ladder, is the Hubble tension. It emerged gradually as both measurements became more precise, and it has been growing over the past decade as the error bars have shrunk faster than the central values have converged. Let me trace the history of the tension, because understanding how it developed helps convey why the community takes it seriously. In 2011, the Planck team published preliminary results suggesting an H0 closer to 68, and the local measurements from the Hubble Key project were centered around 72, with uncertainties of several kilometers per second per megaparsec. The tension was there, but at low significance, roughly 2 sigma, easily within the range. That could be a statistical fluctuation. In 2013, the first Planck full results sharpened the CMB value to 67.4 with a small uncertainty. The local measurements from the SH0 team had also improved. The tension was now at about 3 sigma. The community began paying attention. In 2016, the SH0 team published an improved measurement using the Hubble Space Telescope to observe Cepheids in the Milky Way and in host galaxies of type Ia supernovae. Their value was 73.24 plus or minus 1.74. The tension with Planck was now 3.4 sigma. Papers began appearing proposing modifications to the standard model. In 2019, SH0 published another update with further improved Cepheid measurements, giving H0 equals 74.03 plus or minus 1.42. The tension with Planck was now 4.4 sigma, well into the regime where the physics community takes anomalies very seriously. Conferences and workshops on the Hubble tension proliferated. In 2020 and 2021, the Carnegie Chicago Hubble program published their tip-of-the-red giant branch measurements, giving H0 around 69 to 70. This result was lower than SH0 but still higher than Planck, suggesting that the tension might be somewhat reduced but not eliminated. In 2022, the SH0 team published their most precise result. H0 equals 73.04 plus or minus 1.04, achieving a precision of 1.4%. The tension with Planck was now 5 sigma. This crossed the traditional discovery threshold, not a discovery of new physics, but a discovery that the tension was real. In 2023, the James Webb Space Telescope confirmed the SH0 Cepheid measurements. The systematic that everyone had hoped would resolve the tension was not present. The tension remains at approximately 5 sigma. This progression from 2 sigma in 2011 to 5 sigma in 2022 is not the behavior of a statistical fluctuation or a systematic error that will eventually be identified and corrected. Statistical fluctuations decrease in significance as more data is collected. Systematic errors are typically found when new instruments or new methods probe the same measurement. The Hubble tension has grown with the data, survived new instruments, and resisted the detection of a systematic explanation. This is the behavior of a real anomaly. The tension between these two values is the Hubble tension. It emerged gradually as both measurements became more precise, and it has been growing over the past decade as the error bars have shrunk faster then the central values have converged. The first method is the cosmic distance ladder, the traditional approach to measuring the Hubble constant that traces its origins to Hubble's original work. The distance ladder is a sequence of overlapping methods, each calibrated against the previous, that extends our distance measurements from the immediate solar neighborhood to galaxies hundreds of millions of light years away. The first rung of the ladder is parallax, the geometric method of measuring distances to nearby stars by observing their apparent shift against the background of more distant stars as Earth orbits the Sunday. Parallax gives distances directly from geometry, without any assumptions about the physics of the stars being measured. The Gaia satellite, launched by the European Space Agency in 2013, has measured parallax distances to more than 1 billion stars in the Milky Way with extraordinary precision, providing the foundational calibration for the entire distance ladder. The second rung uses Cepheid variable stars, pulsating supergiant stars whose luminosity oscillates with periods ranging from days to months. There is a tight relationship between the period of a Cepheid's pulsation and its intrinsic luminosity, called the period luminosity relation, or the Leavitt law, after Henrietta Swan Leavitt, who discovered it in 1908. By measuring a Cepheid's period and apparent brightness, and knowing its intrinsic luminosity from the period luminosity relation, the distance can be calculated. Cepheids can be detected in galaxies out to roughly 50 megaparsecs with the Hubble Space Telescope and somewhat further with Webb. The third rung uses type Ia supernovae, thermonuclear explosions of white dwarf stars that have characteristic peak luminosities. Type Ia supernovae are much brighter than Cepheids, visible across billions of light years. By calibrating their peak luminosities, using Cepheid distances in nearby host galaxies, and then measuring their apparent brightness at large distances, the distance ladder extends to the Hubble flow regime, the large-scale regime where the expansion of the universe dominates over local peculiar motions. From the distances and redshifts of type Ia supernovae at large distances, where the linear Hubble law applies, the Hubble constant can be measured. The current best value from this method, as determined by the SH0ES team led by Adam Riess, is H0 equals 73.04 plus or minus 1.04 kilometers per second per megaparsec. The uncertainty is about 1.4%. The second method is indirect, using the early universe as a laboratory. The cosmic microwave background was emitted when the universe was about 380,000 years old, when it had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before recombination, the universe was a hot, dense plasma of electrons, protons, photons, and dark matter. Acoustic oscillations propagated through this plasma, driven by the interplay between the radiation pressure that resisted compression and the gravitational attraction of the matter. These oscillations left imprints in the temperature distribution of the CMB. Regions that were at maximum compression when recombination occurred are slightly hotter than average, and regions at maximum expansion are slightly cooler. The characteristic angular scale of these acoustic oscillations in the CMB is determined by the distance that sound could travel in the early universe plasma before recombination. This is called the sound horizon, and it depends on the early universe physics, specifically on the densities of baryons, photons, neutrinos, and dark matter in the early universe. The sound horizon is a physical scale that we can calculate from first principles if we know the early universe composition. By measuring the angular scale of the acoustic peaks in the CMB power spectrum and comparing it to the calculated sound horizon, we can infer the angular diameter distance to the last scattering surface, the surface from which the CMB photons were emitted. Combined with a model for how the universe has expanded from recombination to today, this gives the Hubble constant The key point is that the CMB method does not measure the Hubble constant directly. It measures the combination of the Hubble constant with the other cosmological parameters through their combined effect on the angular scale of the acoustic peaks and on the expansion history. If the standard cosmological model is correct, the Hubble constant inferred from the CMB should match the Hubble constant measured locally. If they do not match, either the model is wrong or one of the measurements has a systematic error. Now let me tell you about the specific ways in which each method could be wrong and why both possibilities have been extensively investigated without resolution. The local distance ladder could be wrong if there is a systematic error in any of its rungs. The most scrutinized potential source of error is the Cepheid calibration. Cepheids are affected by crowding, the blending of light from nearby unresolved stars that can make a Cepheid appear brighter than it actually is, leading to an underestimate of the distance. They are affected by metallicity, with Cepheids in metal-rich environments potentially having different period luminosity relations than those in metal-poor environments. They are affected by dust, with extinction by interstellar dust reddening and dimming the Cepheids. All of these effects have been studied and corrected for, but residual systematics could remain. The Hubble Space Telescope measurements, performed in optical and near-infrared wavelengths, are more susceptible to crowding and dust than James Webb measurements at longer infrared wavelengths where dust opacity is lower and resolution is higher. This is why the Webb measurements of Cepheids were so anticipated. They would probe the crowding and dust systematics with sensitivity that Hubble could not achieve. The Webb results, published by the SH0ES team in 2023, found that the Cepheid measurements in the host galaxies of type Ia supernovae were consistent between Hubble and Webb within the measurement uncertainties. The crowding and dust corrections applied to the Hubble measurements were found to be correct. The systematic that many hoped would explain the tension was not present. The local value of the Hubble constant remained near 73. But the distance ladder is not the only local measurement. Several independent methods have been developed to measure the Hubble constant without using Cepheids, providing cross-checks against the distance ladder. The tip of the red giant branch method uses a different type of standard candle. When a red giant star reaches a specific luminosity, the helium flash ignites in its core, causing the star to rapidly transition from the red giant branch to the horizontal branch. The luminosity at this transition point, called the tip of the red giant branch, is nearly constant for old, metal-poor stellar populations, providing a standard candle that can be calibrated against Cepheids in well-studied nearby galaxies, and then applied to measure distances independently. The Chicago Carnegie Hubble program, led by Wendy Friedman, used the tip of the red giant branch as an alternative distance indicator to calibrate type Ia supernovae. Their results have been somewhat lower than the SH0ES values, closer to 69 to 70 kilometers per second per megaparsec, though still in mild tension with the CMB value. The comparison between the SH0 ES Cepheid-based result and the CCHP tip of the red giant branch result has itself become a source of discussion, with some analyses finding good agreement and others finding a discrepancy. The situation is more complex than a simple two-value tension. Gravitational wave detections offer an entirely independent method for measuring the Hubble constant. When two compact objects, black holes or neutron stars, merge, they emit gravitational waves whose amplitude depends on the physical properties of the binary and whose frequency evolution traces the orbital dynamics. By measuring the gravitational wave signal, the luminosity distance to the source can be inferred directly from the dynamics without any calibration against other distance indicators. This method is called the standard siren approach, by analogy with the standard candle approach using supernovae. The first standard siren measurement came from the neutron star merger GW 170817. detected by LIGO and Virgo in 2017 and identified with an optical counterpart in the galaxy, NGC 4993. The measurement gave H0 equals 70 plus or minus 12 kilometers per second per megaparsec, consistent with both the local and CMB values, but with an uncertainty too large to distinguish between them. As more mergers are detected, the standard SIREN measurement will become more precise. Current projections suggest that a few dozen neutron star mergers with identified host galaxies will be needed to reduce the uncertainty to the few percent level. That sample is not yet available, but it is accumulating. The CMB method could be wrong if the standard cosmological model is incomplete in ways that affect the inference of the Hubble constant from the acoustic peak pattern. The CMB is not measuring H0 directly. It is measuring a specific combination of cosmological parameters and inferring H0 under the assumption that lambda CDM correctly describes the universe from recombination to today. If lambda CDM is missing an ingredient, the inferred H0 could be biased. Gravitational wave detections offer an entirely independent method for measuring the Hubble constant. When two compact objects, black holes or neutron stars, merge, they emit gravitational waves whose amplitude depends on the physical properties of the binary and whose frequency evolution traces the orbital dynamics. By measuring the gravitational wave signal, the luminosity distance to the source can be inferred directly from the dynamics without any calibration against other distance indicators. This method is called the standard SIREN approach, by analogy with the standard candle approach using supernovae. The standard SIREN method has a profound advantage over other distance indicators. It does not require any calibration. The gravitational wave signal directly encodes the luminosity distance through the amplitude of the waveform and the chirp mass, the specific combination of the two component masses that determines the frequency evolution. No assumptions about the astrophysics of the source are needed beyond general relativity itself. The first standard SIREN measurement came from the neutron star merger GW170817, detected by LIGO and Virgo in August 2017 and identified with an optical counterpart in the galaxy NGC 4993. The simultaneous detection of gravitational waves and light from the same event, called a multi-messenger observation, allowed the team to confirm the host galaxy identification and measure the recession velocity from the galaxy's redshift. The measurement gave H0 equals 70 plus or minus 12 kilometers per second per megaparsec, consistent with both the local and CMB values, but with an uncertainty too large to distinguish between them. The uncertainty is dominated by the inclination degeneracy. The amplitude of the gravitational wave signal depends on both the distance and the angle between the binary's orbital axis and our line of sight. And these are difficult to separate from the signal alone. As more mergers are detected, the standard SIREN measurement will become more precise. Each new event with an identified host galaxy adds an independent distance redshift data point. Current projections suggest that 50 to 100 neutron star mergers with identified host galaxies will be needed to reduce the uncertainty to the 1 to 2% level, where the method could adjudicate between the two values of H0. LIGO and Virgo have detected tens of binary neutron star candidates, but most did not have identified optical counterparts. The third generation gravitational wave detectors, Einstein Telescope and Cosmic Explorer, expected in the 2030s, will detect neutron star mergers with much greater sensitivity and will accumulate the statistical sample needed for a precise standard SIREN measurement. There is also a method that uses the time delays of gravitationally lensed quasars to measure the Hubble constant. When a quasar is gravitationally lensed by an intervening galaxy, the light from the quasar travels along multiple paths around the lens with different path lengths and different arrival times. If the quasar varies in brightness, The same variation appears in each image, but with a time delay set by the path length difference and the Hubble constant. By measuring the time delay and modeling the lens mass distribution, H0 can be inferred. The H0 LICAO and TDC Osmo collaborations have used time delay cosmography to measure H0 from samples of lensed quasars. Their results give values around 73 kilometers per second per megaparsec, consistent with the local distance ladder and in tension with the CMB. More recently, a careful reanalysis by the TDCO-SMO collaboration, incorporating more flexible models for the lens mass distribution, produced a result closer to 74 with a larger uncertainty. The time delay method is independent of the distance ladder and represents an important additional constraint, though it depends on the specific assumptions made about the lens mass distribution. The CMB method could be wrong if the standard cosmological model is incomplete in ways that affect the inference of the Hubble constant from the acoustic peak pattern. The CMB is not measuring H0 directly. It is measuring a specific combination of cosmological parameters and inferring H0 under the assumption that lambda CDM correctly describes the universe from recombination to today. If lambda CDM is missing an ingredient, the inferred H0 could be biased. This is where the proposed solutions to the Hubble tension come in, and where I think the discussion becomes most scientifically interesting. Early dark energy is a model in which a component of dark energy with a density comparable to the radiation and matter densities was present in the universe before recombination and then dissipated shortly afterward. The effect of early dark energy is to increase the expansion rate in the early universe, which reduces the sound horizon. A smaller sound horizon at the same angular scale in the CMB implies a smaller angular diameter distance, which in the lambda CDM model implies a higher Hubble constant. Early dark energy can therefore bring the CMB inferred Hubble constant up toward the local value. The challenge for early dark energy is that it modifies the CMB in specific ways beyond just shifting the Hubble constant, and those modifications must be consistent with the precisely measured acoustic peak pattern. Various forms of early dark energy have been proposed and tested against the CMB data. Some fit the acoustic peaks reasonably well, but they tend to require specific fine-tuning, and they create new tensions with other observations, particularly with measurements of the clustering of matter on large scales. No early dark energy model has been found that resolves the Hubble tension while remaining fully consistent with all other cosmological observations. Interacting dark energy models, in which dark energy interacts with dark matter rather than being purely a cosmological constant, can also shift the inferred Hubble constant from the CMB. The coupling between dark energy and dark matter modifies the expansion history and the growth of structure, and specific coupling forms can reduce the Hubble tension. These models have the advantage of being physically motivated, since there is no fundamental reason why the dark sector components should not interact, but they face similar challenges of creating tensions with other observations. New physics in the neutrino sector has been proposed as another resolution. If there were additional light species in the early universe, described by the effective number of relativistic degrees of freedom n, f, the expansion rate in the early universe would be higher, which would shift the CMB acoustic peaks and change the inferred Hubble constant. Current CMB measurements prefer n, f close to the standard model value of 3.044, but there is enough room in the current uncertainties for small modifications. Future CMB experiments, like the Simons Observatory and CMB S4, will measure NEFF with sufficient precision to test this possibility. Modified gravity at cosmological scales is another class of models. If Einstein's general relativity is modified at large scales or low curvatures, the growth of structure and the expansion history would both be affected. Specific modified gravity models can shift the inferred Hubble constant from the CMB. However, general relativity has been tested to extraordinary precision in the solar system and with gravitational waves, and modifying it in ways that resolve the Hubble tension while remaining consistent with all existing tests is extremely challenging. The DESI survey, which I mentioned in the James Webb Cosmology video, has produced its first-year results on the expansion history of the universe through baryon acoustic oscillation measurements. Baryon acoustic oscillations are the same sound horizon that creates the acoustic peaks in the CMB, now imprinted in the distribution of galaxies in the late universe. Just as the acoustic peaks in the CMB occur at a specific angular scale corresponding to the sound horizon at recombination, the galaxy correlation function has an enhancement at a specific physical scale corresponding to the same sound horizon. By measuring this enhancement in galaxy surveys at different redshifts, the expansion history of the universe can be traced. The DESI 2024 data release, based on observations of more than 5 million galaxies and quasars over the first year of operation, produced the most precise baryon acoustic oscillation measurements yet achieved. The results were analyzed in the context of several dark energy models, including the standard cosmological constant and dynamical dark energy models in which the dark energy equation of state evolves with time. The DESI results showed a preference for an evolving dark energy equation of state over the cosmological constant at a significance of approximately 2 to 3 sigma, depending on the specific model and the data combination used. The preferred model had a dark energy that was stronger in the past and weaker today, a so-called W0WA-CDM model in which the equation of state W equals W0 plus WA times a factor that evolves with cosmic scale factor. This is not a confirmed detection of dynamical dark energy. 2 to 3 sigma is not 5 sigma, but it is the strongest evidence yet from a direct large-scale structure measurement that the dark energy equation of state may not be constant. If confirmed by future DESI data releases, which will include several more years of observations and far more galaxies, it would be the first direct evidence that the cosmological constant description of dark energy is incomplete. For the Hubble tension, the DESI dark energy preference has a specific implication. A dark energy that was stronger in the past would have accelerated the expansion of the universe earlier than the cosmological constant, changing the expansion history between recombination and today. This change in expansion history affects the angular diameter distance to the last scattering surface, which affects the inferred Hubble constant from the CMB. Some analyses find that the DESI preferred dark energy model slightly reduces the tension between the CMB and local H0 measurements, though it does not eliminate it. The combination of the Hubble tension, the DESI dark energy preference, the S8 tension, and the massive early galaxies from Webb is the full picture of where the standard model of cosmology stands in mid-2024. Each individual tension has a potential systematic explanation, but the pattern across multiple independent observations, each showing the universe to be more structured or more rapidly evolving than lambda CDM predicts, is what makes the theoretical community increasingly convinced that something is genuinely missing from the standard model. The DESI survey is still in its early years. Its full data set, expected around 2026, will include measurements of baryon acoustic oscillations at a precision several times better than the current results, and will either confirm or refute the dark energy evolution preference at high significance. The Rubin Observatory, now beginning operations, will provide complementary weak lensing and photometric survey data that will constrain the growth of structure and the S8 tension. The Euclid satellite will provide spectroscopic galaxy survey data that will independently constrain both the Hubble constant through baryon acoustic oscillations and the S8 tension through weak lensing. The next 5 years will be a critical period for the Hubble tension. The combination of data from DESI, Rubin, Euclid, and next-generation CMB experiments will either reveal a systematic error that explains the tension or will confirm it at a level that makes the new physics explanation unavoidable. Now, let me tell you about the development that I find most interesting and most potentially significant, which is the emerging evidence that the Hubble tension may be part of a broader pattern of discordances in the standard cosmological model. The S8 tension is a discrepancy similar in character to the Hubble tension, but involving a different cosmological parameter. S8 measures the amplitude of matter fluctuations, specifically the combination of the matter density and the amplitude of density fluctuations, sigma 8, that is constrained by weak gravitational lensing surveys. The CMB predicts a value of S8 that is slightly higher than what weak lensing surveys measure at a significance of roughly 2 to 3 sigma. Like the Hubble tension, the S8 tension could be a systematic error in the weak lensing measurements, or it could reflect new physics. And like the Hubble tension, it has resisted resolution after extensive investigation. The KIDS, DES, and HSE weak lensing surveys have all found S8 values that are low compared to the CMB prediction. And while the individual significances are moderate, their consistent direction across independent surveys is suggestive of a genuine discordance. If both the H0 tension and the S8 tension are real and not systematic artifacts, they suggest that the standard model is wrong in a way that affects both the late-time expansion history and the late-time growth of structure. This is a specific and testable prediction. Modified gravity models, dynamical dark energy models, and models with dark matter-dark energy interactions can potentially explain both tensions simultaneously, and the pattern of both tensions together provides stronger constraints on potential modifications than either tension alone. The Planck satellite that produced the CMB value of H0 also produced a specific value of the optical depth to reionization, tau, which measures how many CMB photons were scattered by free electrons during the epoch when the first stars reionized the hydrogen in the intergalactic medium. The optical depth affects the amplitude of the small-scale CMB power spectrum. Some analyses have found that different estimates of tau produce somewhat different inferred values of H0, introducing another potential source of systematic uncertainty in the CMB measurement. The combination of these multiple tensions, H0, S8, and smaller discordances in other parameters, paints a picture of a standard model that is under stress at the precision frontier. None of the individual tensions is yet a definitive refutation of lambda CDM. Each has a potential systematic explanation, but the pattern is becoming harder to dismiss, and the theoretical community is increasingly taking seriously the possibility that new physics is required. What specifically would that new physics be? The constraints are severe. Any modification must preserve the extraordinary success of lambda CDM in explaining the overall CMB power spectrum, the large-scale structure of the universe, and Big Bang nucleosynthesis. It must produce a Hubble constant near 73 when inferred from local measurements, while appearing to produce a Hubble constant near 67.4 when inferred from the CMB. And it must not create new tensions with the many other observations that lambda CDM explains successfully. This is a very narrow target. Every proposed solution that has been evaluated carefully has been found to either fail to resolve the tension sufficiently or to create new tensions elsewhere. The space of modifications that could work is not empty, but it is much smaller than it appeared before the tension was precisely characterized. I want to say something about the significance of the James Webb Space Telescope's role in this story beyond the specific Cepheid measurements I described earlier. Webb has not only confirmed the local distance ladder measurements, it has opened new windows on the early universe that are themselves producing data bearing on the tension. The massive early galaxies that Webb has found, more massive and more numerous at high redshifts than Lambda CDM predicts, are connected to the Hubble tension through the early universe physics. Both anomalies suggest that the early universe was different from what Lambda CDM describes. The specific form of the difference is not the same in both cases, but the direction is consistent. The early universe was more structured, more rapidly evolving, more active than the Standard Model predicts. A modification to the Standard Model that explains the massive early galaxies might also explain the Hubble tension, or at least might be part of a broader modification that does. The DESI survey, which I mentioned in the James Webb cosmology video, has produced its first results on the expansion history of the universe through baryon acoustic oscillation measurements. The DESI data prefer a dark energy equation of state that has evolved over cosmic time rather than remaining constant at the cosmological constant value. If this preference is confirmed by more data, it would be the first direct evidence that the cosmological constant description of dark energy is incomplete, and it would have specific implications for the Hubble tension. The DESI results, if confirmed, do not by themselves resolve the Hubble tension. But they do suggest that the dark energy sector is more complex than Lambda CDM assumes, and a more complex dark energy with specific time evolution could in principle shift the inferred Hubble constant from the CMB toward the locally measured value. The theoretical framework for connecting the DESI results to the Hubble tension is being actively developed. Let me close with my honest assessment of where the Hubble tension stands, because I think the honest picture is more nuanced than either the hype or the skepticism that surrounds it. Let me close with my honest assessment of where the Hubble tension stands, because I think the honest picture is more nuanced than either the hype or the skepticism that surrounds it. Let me start by acknowledging something that I think is important and that does not get said enough in popular discussions of the Hubble tension. The history of cosmology in the 20th century is a history of the Hubble constant being wrong. Hubble's original value of 500 was too high by a factor of 7. The controversy between Sandage and de Vaucouleurs lasted decades and was only resolved by the Hubble Space Telescope. The key project value of 72 in 2001 seemed definitive, but has since been revised upward. The history of this constant is a history of systematic errors being discovered and corrected. It is therefore legitimate to ask whether the current local measurements are right and the CMB measurement is the one with the error, or whether the local measurements have an undiscovered systematic. The history suggests humility about measurements that seem secure, but the specific nature of the current measurements makes this explanation increasingly hard to sustain. The systematic that would explain the tension must be present in the distance ladder measurements, but absent from the CMB measurement. It must not have been detected by the various cross-checks that have been performed, including the Webb observations. It must produce a bias of approximately 8% in one direction without producing a corresponding bias in any other observable. This is possible, but as the measurements improve and the cross-checks multiply, the space for such a systematic shrinks. The theoretical models that might resolve the tension through new physics have all run into difficulties. Early dark energy is the most studied and faces the most severe constraints from CMB and large-scale structure observations. Other models face similar challenges. The space of modifications that could work is not empty, but it is much smaller than it appeared before the tension was precisely characterized. What I find most compelling about the situation is not any individual measurement or model, but the pattern. The Hubble tension, the S8 tension, the massive early galaxies, the DESI dark energy preference. Each of these is individually explainable by systematics or by statistical fluctuations at plausible levels. But they all point in the same direction. The universe is more structured, more dynamically active, more rapidly evolving than lambda CDM predicts. The consistency of the direction across independent observations at different scales and epochs is what makes the pattern worth taking seriously. If I had to place a bet, I would bet that we are in the early stages of the next major revision to the standard cosmological model. Not a revolution that overturns everything we know, a refinement that adds new physics to the dark sector, modifying the dark energy or the dark matter sector in ways that resolve the tensions without destroying the model's successes. But the specific nature of the modification remains unknown, and it may not be found without a confirmed detection of the kind that the James Webb, DESI, Rubin, and Euclid surveys are positioned to provide. The Hubble tension is real. Both measurements have been checked extensively. James Webb has confirmed the local measurement. The model that connects them is lambda CDM, the standard model of cosmology. Lambda CDM has been extraordinarily successful. It explains the CMB power spectrum, the large-scale structure, the accelerated expansion, the Big Bang nucleosynthesis abundances. Any replacement must preserve these successes while accounting for the tension. This is a severe constraint. The systematic that might explain the local measurement away has not been found. Webb looked for it and did not find it. The alternative local distance indicators give values that are somewhat lower than the SH0ES result, but still higher than the CMB value, which does not resolve the tension but complicates the picture. The gravitational wave standard SIREN measurements are not yet precise enough to adjudicate. The theoretical models that might resolve the tension through new physics have all run into difficulties. Dozens of modifications to the standard model have been proposed as potential solutions to the Hubble tension. Let me describe the most carefully studied ones in enough detail to understand why they have been found wanting. Early dark energy is a model in which a component of dark energy with a density comparable to the radiation and matter densities was present in the universe before recombination and then dissipated shortly afterward. The effect of early dark energy is to increase the expansion rate in the early universe, which reduces the sound horizon. A smaller sound horizon at the same angular scale in the CMB implies a smaller angular diameter distance, which in the lambda CDM model implies a higher Hubble constant. Early dark energy can therefore bring the CMB inferred Hubble constant up toward the local value. The physical motivation for early dark energy comes from axion-like particles. If there is a light scalar field similar to the axion but with a potential specifically designed to produce significant energy density near recombination, the field can behave like dark energy in the early universe and then redshift away as the universe expands. Mark Kamienowski and Vivian Poulan developed influential models of early dark energy that became the most studied proposal for resolving the Hubble tension. The challenge for early dark energy is that it modifies the CMB in specific ways beyond just shifting the Hubble constant. The increase in the early expansion rate also shifts the phase of the acoustic oscillations and changes the amplitude of the CMB peaks in specific ways. The modified Boltzmann codes used to predict the CMB power spectrum for early dark energy models must match not just the overall peak positions, but the detailed shape and relative heights of all the peaks. And they must match the measurements from Planck across all angular scales. When the early dark energy models are fitted to the Planck data, they can produce a Hubble constant closer to 73, but at the cost of specific tensions with other cosmological observables. The amplitude of matter fluctuations on small scales is changed in ways that create a larger S8 tension. The baryon acoustic oscillation measurements from large galaxy surveys, which are an independent standard ruler, are changed in ways that create tensions with the BOSS and eBOSS survey data. The constraint that all these observations must be simultaneously accommodated severely limits the parameter space of early dark energy models. The most recent analyses suggest that early dark energy while it can reduce the Hubble tension, cannot fully resolve it while remaining consistent with all existing cosmological observations. The remaining tension after including early dark energy is smaller but not zero, and the additional tensions it creates are as concerning as the original Hubble tension. Interacting dark energy models, in which dark energy exchanges energy with dark matter, rather than behaving as a pure cosmological constant, can also shift the inferred Hubble constant from the CMB. If dark energy is gaining energy from dark matter in the late universe, the expansion history is modified in ways that change the relationship between the CMB acoustic peaks and the current expansion rate. Various coupling forms have been proposed, and some can reduce the Hubble tension. But these models also modify the growth of large-scale structure in ways that create tensions with weak lensing surveys. New physics in the neutrino sector has been proposed as another resolution. If there were additional light species in the early universe, described by the effective number of relativistic degrees of freedom n, f, the expansion rate in the early universe would be higher, which would shift the CMB acoustic peaks and change the inferred Hubble constant. The standard model predicts NEFE equals 3.044, accounting for the 3 known neutrino species with their thermal history. Current CMB measurements prefer NF close to 3.044, but there is enough room in the current uncertainties for a small modification of about 0.3 to 0.5 in NF. A value of NF around 3.5 to 3.7 would bring the CMB inferred H0 close to 73, but this requires new light species beyond the standard model. The Simons Observatory and CMB S4 next generation CMB experiments will measure NF with a precision of about 0.03 compared to the current Planck precision of about 0.17. This measurement will either confirm the standard model prediction of 3.044 or detect a deviation consistent with new light species. This is one of the clearest tests of a specific proposed resolution to the Hubble tension that future experiments will be able to perform. Modified gravity at cosmological scales is another class of models. If Einstein's general relativity is modified at large scales or low curvatures, the growth of structure and the expansion history would both be affected. Specific modified gravity models can shift the inferred Hubble constant from the CMB. However, general relativity has been tested to extraordinary precision in the solar system with gravitational waves and through measurements of the Shapiro delay and the orbital decay of binary pulsars. Modifying it in ways that resolve the Hubble tension while remaining consistent with all existing tests is extremely challenging. The constraints from the nearly simultaneous arrival of gravitational waves and photons from GW 170817, which constrains the speed of gravitational waves to equal the speed of light to better than 1 part in 10 to the 15th, rule out many modified gravity models that had been considered viable. Early dark energy is the most studied and faces the most severe constraints from CMB and large-scale structure observations. Other models face similar challenges. The most honest statement is this: the Hubble tension is an unresolved anomaly in the best tested theory of the universe we have ever constructed. It has resisted resolution for a decade. It has survived the most careful scrutiny of both the measurements and the model. And it is getting worse rather than better as measurements become more precise. This is what progress in physics looks like when it is happening at the frontier. Not a clean discovery with a clear implication. An anomaly that accumulates, that resists explanation, that gradually forces the community from dismissal to puzzlement to the recognition that something genuinely needs to be rethought. The Hubble tension is in that middle stage right now. The recognition is spreading, the rethinking has begun, but the specific resolution has not been found. The number does not match. We do not know why, that is one of the most exciting sentences in science. If this changed how you think about the standard model of cosmology, if the Hubble tension looks different after understanding both measurements and their implications, tell me in the comments. Tell me which proposed solution you find most compelling and why you think it is likely or unlikely to pan out. Tell me whether you think the tension will be resolved by discovering a systematic error in one of the measurements or by discovering new physics. And tell me whether you find the combination of the Hubble tension, the S8 tension, the massive early galaxies, and the DESI dark energy hints pointing toward the same conclusion, or whether you think they are independent anomalies that will dissolve independently. These are the most important questions in cosmology right now. And subscribe if you want to stay at the frontier, where the number that does not match is pointing us toward whatever comes next